Hello everyone, welcome to Math Fables, and today we are here with our very first topic explanation video, which will be on the chapter Vectors. Vectors is probably the hardest chapter that every person that I have met, or almost every person that I have met, has stated from Further Pure Mathematics of subject code 9231. And the reason of this is because there are so many different concepts to grasp, and there are so many varieties of approach to the same sums that it makes us quite confused, right? So, here today, I am here with a very structured framework on how you can proceed with the chapter so that it is very easy and simplified for you. So this entire explanatory session on vectors will be divided into two parts. So in this video, which is the first part, I will be explaining the concepts and the basic understanding of vectors that you need to have. And for the second video, we will be focusing on the calculations, the different kinds of formulas that we need and how to use them in different scenarios. Okay. So to begin with, at the very first, we need to know what is a vector, which is anything with a magnitude and a direction. So this is a definition that you know from at least class 8 or 9, right? So the next thing that we need to understand in this chapter is lines, which is two dots when they are stretched infinitely in either direction, then we get a line, right? And then you need to understand certain things that you already know. So I'm not going to go in depth with them. That is, lines can be of two types. They are either parallel or they're intersecting. So to get started, so if I say, so this is our line, right? So here we have a line. And if we are to draw another line, which all points are equally spaced from the previous line, then they are parallel. But however, if it was any less in any side, even a little bit, right, then they are not parallel, because then what happens is that they become intersecting. So although over here it doesn't look like they're intersecting, but if you extrapolate them, you will see that they become intersecting at a point, right? So lines can only be of two types, that is, they are either parallel or they're intersecting. But things become more complicated when you introduce a plane. Okay, so a plane is an infinite two-dimensional surface. So how do we define a plane? We define a plane with the equation of a plane. So to find out the equation of a plane, there are some basic criteria that you need to have. Otherwise, you cannot find the equation of a plane. So we can have many different starting points through which we go to the equation of a plane, right? So what are these minimum criteria? Number A, we need a point on the plane and a normal to the plane. So now you might be asking that what is a normal? So in very simple terms, a direction vector perpendicular to the direction of the plane is a normal. So for example, over here, you see this N that I have marked is perpendicular to the plane, which is the rectangle, right? Because it is protruding out from the plane. Though it is hard to show in a 2D diagram, but you get it, right? So there we have our normal, and it is always denoted by small n, and a plane is denoted by this symbol, which kind of looks like an rotated C that you can see over here. So that's it. So the second minimum criteria that we can have is a normal to the plane and the distance of the plane from the origin, which is the 0, 0 point, right? Number C is that we need three given non-collinear points. So what are collinear points? Collinear points are points which lie on the same line. So we cannot have all three collinear points. We need three non-collinear points. And then our last method through which we can go and find the equation of a plane is if we have two concurrent lines. So what are concurrent lines. Concurrent lines are any lines that intersect at an angle to at a single point, right? So concurrent lines basically means intersecting lines, which is the opposite of parallel lines. So now, what are the different forms of the equation of a plane? So the equation of a plane can be defined in the scalar product form. Then we have number 2, the standard form. We have number 3, the Cartesian form, and number 5, the parametric form. So moving to our very first, which is the scalar product form. So if R is the position vector of any point on the plane, N is the normal vector to the plane, and A is the position vector of a given point on the plane, then the normal is perpendicular to the plane. That is the criteria for it to be a normal in the first place, right? So normal is perpendicular to the plane. And if normal is perpendicular to the plane, normal will also be perpendicular to any line on the plane, because any line on the plane has the same direction vector as the plane. So AP over here is a line on the plane which is perpendicular to the normal. So why did we need to know the position vectors of 2 points A and P? It is because otherwise we wouldn't have been able to find AP, right? The direction vector AP. So through the triangle rule, we know AP is OP minus OA. So R minus A. And this direction is perpendicular to the normal. Now, if AP is perpendicular to the normal, AP dot N, so we're doing the dot product over here, equals 0. Now that is something that you have learned from P3. And what is the scalar product? So I'll show you what is the scalar product in just a bit. So scalar product basically means if you have, for example, 1, 2, if you have 1, 2, 3, and you're doing the dot product with 4, 5, 6, then you have a rule onto what will the product be, right? So how do we find the product of this two? That is found by the scalar product. So for that, what we do is, for the very first one, we multiply this and then we subtract this. So we go in a crisscross motion. So that is 2 into 6, 12 minus 15. So that is 1. For the second one, similarly, we will keep 2 and 5 aside, and then we will multiply 1 with 6 and 3 with 4. So 6 minus 12 is minus 12. And then for the very last part, we will again repeat the same thing but with the top two ones. So that is 5 minus 8 is minus 3. However, over here what you need to do always is you have to multiply a minus sign with the one of the y coordinate, you can say, or the ij for the ijk system, that is the j. So I j k for x y z, right? So with the I or with the j or the y, you always multiply the minus 1. So the answer is 1, 12 minus 3. So that is our scalar product. Okay. Now, so there, if the two direction vectors that we are multiplying to find the scalar product are perpendicular to each other, the answer is always 0. So over here, AP, we can substitute AP with R minus A. So when we do the dot product with N, the answer is 0, right? So 0 will also, this will also, if you now cross simplify, by cross multiplying, we have Rn minus An is equals to 0. So Rn is equals to An. Now this An is denoted by a constant which we call the scalar constant. So Rn equals to D. So when you do scalar product, as you have seen, you always get a value, right? So that is our D over here. So if we multiply any vector with the normal, the vector of any point on the plane, so it can be of A, it can be of P, it doesn't really matter. So if we multiply that with the normal, we always get the same constant, which is the scalar constant, or D. Now we have our second form, which is the standard form. So for the standard form, what we do is that we describe it in terms of the perpendicular distance from the origin to the plane. Okay? So for that, how do we derive it? We start from the result that we got of the previous form, which is the scalar product form, and then we divide both sides with the magnitude of normal. So how do we find the magnitude of normal? So here is how we find the magnitude of the normal. So let's say the normal has a direction vector of 2, 1, 3. Okay. So how do you find the magnitude of this? It's 2 square plus 1 square plus 3 square. Okay. Plus 3 square. So it will equal 4 plus 1 plus 9. So root over 14 is the magnitude of our normal over here. So this is what we're denoting by modulus n. Okay. So for the standard form, we divide both sides with the modulus of n, and what we get is the unit vector of the normal. So the unit vector of the normal into R is equals to the unit vector of A into a unit vector of n into A. So this one is denoted by a separate constant D, which is the perpendicular distance from the origin to plane, or the length of projection of A on n. So what is a projection? Projections are not in our syllabus, but knowing the basic concept about projections always help to understand the concepts of vectors. So I will be describing them briefly at the end of this video. Okay. So different values of D give different parallel planes. If Rn equals to 0, then the plane passes through the origin. So what do they mean by different values of D give different planes? So let's give another visual example of it. So let's say here is our origin, which is O, right? And here you have a plane. And now here you have a plane. Now, as you can see, these two planes are parallel, right? I apologize since for the lines not being straight. So if they are parallel, obviously their normal will have the same direction. They will have the same normal, right? But what is making the two planes distinct from each other is their distance from the origin. So while this distance is d1, this distance is d2. So this is how we can describe our plane, right? So if the distances are different, what we get is two parallel planes which are at different distances from the origin. That is only when the equation of the plane itself is constant. If the equation of the planes were different, then they are not parallel planes, then they are intersecting or they are skew. There are many different things that can happen with that. We will learn about them shortly. So then we have the Cartesian form, which is one of the most common forms that comes in our exam, I would say, if not the most common. So the Cartesian form and the parametric form, these two are the most commonly used ones in our CAIE exams. So the form is basically where you are representing the equation of the plane in terms of x plus y plus z, okay, and they will have different coefficients which equals d. Now a, b, c, these coefficients refer to the normal. So if you have a normal of 2, 1, 3, then it will be 2x plus y plus 3z equals to d. And we already know what is capital D. That is the scalar product that we find, okay? By multiplying any point with the normal, the scalar constant that we find, that is d. The fourth way is the parametric form, which is not unique. So if r is the position vector of any point on a plane, d and e are non-parallel vectors parallel to the plane. A is the position vector of a given point on the plane, and lambda and mu are independent constant, then r equals to a plus lambda d plus mu e. So now let me explain to you what is happening. So let's say we have a plane like this, right? And over here, any line that lies on the plane is parallel to the plane. So let's say we have this line on the plane, and we have this other line on the plane. Okay. I have mistakenly drawn an arc though. Let me fix it. Okay. So now, as you can clearly see, these two lines are not parallel. They are intersecting. But since they are all contained within the plane, they are parallel to the plane. Okay. So let's say the direction vector of this line is D. The direction vector of this line is E. Then how can we describe the plane? So we need the direction vector of this line, we need the direction vector of this line, and we need any point on the plane, any random point. So this can be our point A. However, this point can also lie on one of these lines, right? So it can lie on the line with the direction vector D, or it can lie on the line with the direction vector E. Then what happens is that the equation of a plane will be R. R is the equation of a plane. You state the position vector of this point. So let's say the position vector is 1, 2, 3 plus you introduce a constant. So you do not need to find the value of this constant. So you introduce lambda, which are constant, and then you have the direction vector, which is 4, 1, 5, 6 plus mu, which is another constant, let's say 4, 2 minus 1, and that is our equation of the plane, right? So over here, why do we introduce the lambdas and the mu's? It is because, let's say we found the direction vector D to be 2, 4, 6, right? So we know that the line does not end here. When you stretch it, it goes infinitely, right? It goes infinitely, it moves out. So since it is not a constant, we do not know exactly the magnitude of D. It cannot be known over here in this instant. So what do we do over here? We just take common and we write the simplest expression. So now it can be 2, it can be 3, it can be 4, it can be anything over here. So instead of this constants, we just introduce a constant, independent constant, and this is 1, 2, 3. So we describe it like that. Okay, so that there goes our parametric form. Now, if R is the position vector of any point on the plane, A, B, and C are the position vectors of three given points on the plane, and S, T, and U are independent constant, where S plus T plus U equals to 1. This one is actually not important for our CIE syllabus. We will stick to the first one, okay? Now we have the equations of axial planes. Now, this is purely for your understanding, to build up your concepts. And when I say that it actually helps, it actually does help. Okay, so you need to know about this, but they will never ask you to write equation of an axial plane. They'll never tell you to define what is an axial plane. Okay, so you do not even need to know what is an axial plane. So over here you can see that axial plane is a plane which only is lying on two particular dimensions, right? Over here it is lying on the xy plane. So you might ask, how could it have not been an axial plane, right? So it could have been not been an axial plane if, let's say, the plane was slanted like this. So you can see that it covers um this one is slanted, but it is like slanted in a 3D way, right? So it is crossing all three planes. It will cross the y plane, it will cross the z plane, this is the x plane. So over here an axial plane is one which is only lying on one of those three planes. Okay, moving on. So for the xy plane, the scalar product form. So anything that you multiply with the normal. So for the xy plane, the normal will obviously be in the direction z, right? Because we know the directions of x, y, and z are all perpendicular to each other. So for the scalar form, if the normal is the z-axis. So the simplest way to define the z-axis is 0, 0, 1. So we are using the simplest ways, right? So if we multiply anything with the normal, the answer we get is 0. What is the Cartesian form? In the Cartesian form, z will be equals to 0. For the parametric form, we have r equals to, since it passes through the origin, so no need to write 0, 0, 0. That was our a, the point a, plus lambda, then the direction of the x-axis, plus mu, the direction of the y-axis. So that's how we are defining it. Now moving on to the YZ plane. So if the plane lies purely in the y and z direction, then obviously the x-axis is the normal, and the simplest way to define the normal is 1, 0, 0. And if we multiply the normal with r, the product we get is 0. So then we have our Cartesian form, x equals to 0. And then the parametric form, again, it passes through the origin. Over here, in this diagram, the intersection of the x, y, and z axis represents the origin, by the way. So then there is no need to again mention the point of the origin, which is 0, 0, 0. So we are just eliminating that, plus the direction of the y-axis, which is 0, 1, 0, plus constant into the direction of the z-axis, which is 0, 0, 1. And then we are doing the same for the xz axis, right? So you can see the normal here is 0, 1, 0. Here you have the scalar product form, the Cartesian form, and the parametric form.